In this video we are going to talk about polarity. There are, under covalent bonds, nonpolar covalent bonds as well as polar covalent bonds. With nonpolar, electrons are shared evenly, versus with polar covalent bonds, electrons are shared unevenly. And I have to caution you, as students typically confuse the definitions, meaning they attach this meaning with polar and this meaning with nonpolar. But this means no poles versus this one means poles. If they're shared unevenly, there's going to be opposite ends or positive and negative ends to that molecule, versus no poles, meaning that the overall molecule is not going to have a charge associated with it. So for a molecule to be nonpolar covalent, the electronegativity difference is essentially zero between the two atoms, or the molecule is symmetrical in both the x and the y direction. It has to be symmetrical in both to be considered nonpolar. Otherwise, if it's only symmetrical in one, it's considered polar. So for an example, classic example is methane, which is CH4. If we were to draw out methane, the electronegativity difference between C and H, they're not the same atoms, so it's not zero. So that first one doesn't apply. However, this molecule is symmetrical. If you were to build it with a kit or actually draw it three-dimensionally, it is symmetrical in the x direction as well as in the y direction. If you fold it in half in either direction, it does look the same. So this second bullet applies. For an example of this first bullet, we could use oxygen. So O2 is a diatomic molecule. The difference between these two as far as electronegativities, as they are the same atom, you don't even need to look up the electronegativities. The difference between the two has to be zero, so this has to be a nonpolar covalent bond. So these electrons that are shared between this oxygen and this oxygen are being shared evenly. With polar covalent, they are shared unevenly. So either the electronegativity difference is not zero or the molecule is not symmetrical. For an electronegativity difference that's not zero, hydrofluoric acid is a good example. We'll draw in the lone pairs. As far as electronegativity, the trend is, looking at the periodic table, goes like this, if you remember back to periodic trends, with fluorine being way more electronegative than hydrogen, which is located over here, if this area was our periodic table. So fluorine is the most electronegative atom. It is going to share these electrons with hydrogen, but it is not going to share them evenly. These two electrons are going to be closer to fluorine most of the time than hydrogen. With a bond, electrons move around all the time randomly, but they are most often going to be found near fluorine. As electrons have a negative charge, and these negative electrons are going to be associated over here more than over here, that means hydrogen is going to end up with a slightly positive charge, and fluorine is going to end up with a negative charge. So if you were to draw the arrow where the negative end of the molecule is, you would draw something that looks like this. It's an arrow with a little hash mark at the end. And how I help myself remember is that this end, if you were to cut it off right here, looks like a plus sign. And the plus sign is always near the positive end of the molecule, where the pointed end goes towards the negative end. It tells you that this side is negative and this side is positive. An example of a molecule that is not symmetrical in both directions is water. So we can draw out water. And at first glance, you're going to say, yeah, it's symmetrical. And it is in this direction. If we were to fold this H, it would nicely fold over here, and it would look exactly the same. However, However, in the other direction, it's not. And the way I drew it, it's really hard to tell that it's not symmetrical. For purposes of determining polarity, especially when you have a molecule that looks like this, it's really helpful to use the atom kits and actually build it. So I drew it as a Lewis dot diagram. If I was to redraw it in the bent shape that it actually is, it would get drawn like this. In here, it's easier to tell that in one direction it's symmetrical and in the other direction it's not. So for polarity, if you need to determine whether something is polar covalent or non-polar covalent, and it's not something like methane where all four ends are exactly the same, they're all hydrogens. If you have some lone pairs with some other atoms, I highly recommend grabbing an atom kit and building it. Because unless if you can picture what the molecule looks like three-dimensionally in your head, it's really hard to tell. So water is a good example of kind of needing to build out the molecule and see. But that is how you determine polarity.